Hello and welcome. Introduction. In this video, I'm going to show you how to use the UART communication module of the TM4C123GH6PM microcontroller to display a simple message. Now, initially I planned to include this in part 1. But then I felt that it would make the video too long. So I've decided to make a separate video. The hardware and software setup. Now the hardware setup is identical to the previous video. By that I mean the part 1 of this UART series. So in this video, I will briefly go over the setup again. So here I have the TM4C series board, a mini breadboard here, some male to female jumpers, the USB to TTL adapter cable, the logic analyzer. Now the connections. Now PE5 of the TM4C series board, here, this green jumper cable. So PE5, that is the transmit pin on this board. All right, so this PE5, the transmit pin, is connected to the receiving cable or pin of the USB TTL adapter cable. And then PE4, which is the receive on the receive pin on the TM4C series board, that is connected to the transmit cable or pin of the USB TTL cable. And then the ground of the USB TTL cable and the ground of the TM4C series board are connected. And then the transmit pin, right, is from the TM4C series is connected to channel D0 of my logic analyzer. And then not forgetting the ground of the logic analyzer that has to be connected to the ground of the TM4C series board and also the USB TTL adapter cable. And finally, not forgetting the USB 2 micro USB connecting here. This one has to be connected to via the cable to your laptop or desktop. The program. Complete listing. Now the program that I'm going to use in this video is almost identical to the program I used in my previous video. By that I mean I'm referring to part 1 of the UART series. So I'm going to assume that you are familiar with the program used in part 1. Now, if you're not familiar with the program in part 1, please watch that video first and come back to this video. It is important that you understand the program in part 1. The program explanation. So, as I mentioned earlier, the program that I'm presenting in this video is identical to the program that I used in my previous video. But there are some new parts, especially the main frog subroutine that I mentioned earlier. So in this video, I will briefly cover the parts that I covered in my previous video and give more attention to the parts that are new. All right, so here is the initialization section, and what follows are the definition of all the registers that are used in the video. Okay, so here is the main prog routine, and it starts from here all the way down here. So this whole listing of instructions is the main prog routine. Now, before I go any further, I'd like to compare this main prog routine that I've just shown you with the one that I've used in my previous video. So this is the main prog routine that I've used in my previous videos. So if you can see, the current main prog routine that I'm using uses a string data or data array that is stored in this thing called char table, whereas in the previous main prog routine, I display the message a word at a time, a character at a time. So the routine will just get hold one character and then transmit it, get the next character and transmit it, and so on. Whereas this one here, I use a data array. I'll show it to you in a few moments. Hey, so we are back to the main prog routine. Now, so I just want to highlight these three instructions here. These are basically three subroutines. So the first instruction here, BL is branch with link. And before I go any further, viewers of this channel probably will recognize these three subroutines. They are used in my previous program. Okay, so back to this BL enable clocks. Basically, this will call this subroutine and enable the clocks. Then BL initialize UART5. This instruction will initialize the UART5 module, and then the third BL instruction, configure UART5, will configure the UART5 module. Next, these two instructions here, basically we set up R4 with the base address of the character table. So the first instruction here, the load instruction, will copy the address of the char table. Char table will be assigned the address of the table itself. So that address, whatever that address is, will be copied or loaded into register R4. Now, char table is, as I mentioned a few moments ago, is a memory location where the string data or the data array is stored. Now, let me just skip all this for the time being and go to the part of the program where we can see the char table. So let's go to that part of the program briefly. So here it is. So here we have the char table, and the assembler will assign the address to this label here, and this goes under this area directive, area my data, data, read only. This line here declares a read-only data section, which I call my data. Now, you don't have to call it my data. You can call it anything else you wish. And then DCB defines the string hello world, and we have followed by hex 0D, that is a carriage return, and then hex 0A, that is a line feed, and then the 0, which is a null terminator, marking the end of this string. All right, so this is the char table. So let's go back to the main proc routine. Okay, so now we're back to the main proc routine, and let me just look at this MOV R5 comma #0. Basically, this copies or load decimal 0 into register R5. Basically, this instruction here initialize R5 to 0, and R5 is used as a counter. So we come to this part here that is in the red box. So loop underscore table, this label here basically marks the beginning of the loop, this loop here, that goes through the string of characters that we've seen earlier. So this instruction, LDRB, R0 comma square bracket R4 comma R5 close square bracket. Now this LDRB is actually load a single byte. B here stands for a byte, 8 bits. All right, so load a single byte from memory address into R0. Now the memory address is actually calculated from the contents of R4 and R5. By that I mean, so R4 basically will contain the base address of char table, and R5 will contain the offset or the index of the current character in the string. All right, so if you add them up, the contents of R4 add the contents of R5, not adding the register itself, but the contents of the registers will give us the address of char table. So that address is copied or loaded into R0. Now, before I go any further, let me clarify this instruction here. The LDRB R0 comma open square bracket R4 comma R5 close square bracket. Now to explain this instruction, let me just recall the char table. So then let me zoom in to this part here. Now char table would be assigned an address. That address would be called the base address, and this base address is actually assigned by the assembler. All right, and each character in the string, all right, which are represented here, is referred to as the index of a string. All right, as in a single array, the index, or in this, I have called it the offset. So the resulting address that is copied into R0 is actually the sum of base address plus the index or offset. Now, for example, take this uppercase H. The address of this uppercase H would be the base address plus the index. So that would give us the address of uppercase H, and that would be the address that is copied into R0. Now, the next character would be the base address, add or plus the index of this lowercase e. and that would be copied into R0. And this B loop underscore table will send it back here and keep doing it until you reach the null terminator. Okay, so this add add instruction, add R5, R5, #1. Basically, this will increment the contents of R5 by 1. That basically moves to the next character in the string. Then we come to the CMP compare instruction. So CMP R0, #0. So the contents of R0 is compared with this decimal 0. Basically, this is to check for the null terminator that marks the end of the character string. Remember the hello world string? So, and there is a 0 at the end of the string. That 0 is known as the null terminator. So this instruction would check for the null terminator. So BEQ will branch to the done label, which is here, if the comparison, this comparison here, finds that R0 contains the 0. If R0 contains the 0, which indicates that it has come to the end of the character string. When that is accomplished, then the BEQ instruction will be executed and the control of the program goes down to this point here, the done. If not, then it will transmit. It will branch to a subroutine called UART underscore transmitter. All right, so this basically, this subroutine here will transmit the character to the serial output. And here it will branch back to the loop table label. So it will keep going round this loop. And then finally, we come to this part here, the label done. When this label is reached, when it's a BEQ, when it's checked, when the contents of R0 is a 0, it will come here. Basically, that indicates that the null terminator is found, and the next instruction is executed. Now this one, B, is branch, and space and dot. Can you see this dot here? That dot here basically is a shorthand or short form for current instruction. So that this B space dot here basically stands for branch to the current address. Basically, this will give us an infinite loop that will prevent the program from exiting. And then ENDP here indicates the end of the whole routine. Hey, so this is the enable clocks proc subroutine. And the main purpose of this whole subroutine is to enable the clock to the UART5 module, and also to enable the clock to the GPIO port E. Now, I've covered this subroutine in my previous video in detail, and if you are new to this channel and you want to know more, you might want to consider watching my previous video. Here, I will just briefly go over the subroutine. And here is the initialize UART5 proc subroutine. And basically, this set of instructions here disable the UART5 module, and here these instructions will set the integer part of the baud rate, and here this part, these instructions will set the fractional part of the baud rate. Again, I am just briefly going over this. I've covered this in my previous video in more detail. And here we have the these instructions here will select the system clock. And here these instructions will set the data length. In this case, there's the data length is 8-bit, no parity, and no first in, first out. And then finally, we have to enable the UART5 module. Previously, at the start of this particular subroutine, we disable it. Now we enable it. And this here, BXLR instruction will return the control back to the main proc routine. And here ENDP signifies or marks the end of the initialized UART5 proc subroutine. Okay, so this is the configure UART5 proc subroutine. These 4 instructions here will set PE4, that is port E bit 4, and PE5, that is port E bit 5, as digital functionality. It means we want to enable the digital I/O functions for these 2 bits. All right, so that's the responsibility of these 4 instructions. Then followed by these 4 instructions, these instructions will enable the alternate function for PE4 and PE5. Remember, these bits here can function as GPIO I/O function, or in this case, we are using it for UART operation, which is the alternate function. So we need to enable the alternate function. Then these 3 instructions will disable the analog functions. And then these 3 instructions will configure PE4 and PE5 for UART functionality. And BXLR here will return the control back to the main proc routine. ENDP signifies the end of the proc subroutine. And then here we come to this UART5 _ transmitter proc subroutine. So this is responsible for transmitting data to the serial terminal using the UART5 module. So these instructions here will wait until the TX buffer or the transmit buffer is empty. All right, and then these 3 instructions, LDR, these 2 instructions, LDR and STR, transmit the character in register R0. And BXLR, as we've seen earlier, basically returns the control back to the main proc routine. And align directive here is used to ensure that the code, all right, is aligned on a word boundary. What that means is a 4-byte boundary for proper performance and efficiency. And then the ENDP here marks the end of this subroutine. And we've covered this character table here earlier. And END here marks the end of the entire program. Demonstration. So this is the hardware setup. I've gone over this in the earlier part of this video, so I won't go over it again. I just want to show you this is this is the setup. And here's a picture of my actual hardware setup. Okay, so let's move over to the Kyle Microvision IDE. Okay, so here we are in the Kyle Microvision IDE, and I've set up the IDE and I've uploaded the code here. So let me just very briefly go through it. So here is the initialization part. Here is the declaration of the registers used in the program. And here is the main proc routine that we talked about earlier. And then here is the enable clocks proc subroutine. And here is the initialize UART5 proc routine. Goes all the way down here. And then here is the configure UART5 proc subroutine. And then here we have the UART5 underscore transmitter proc subroutine. And here is the area designated to store the character array. And here is the end, 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 to indicate the end of the entire program. So that's the program. Let me just go to project and do a build target. And we have no problems, 0 errors, 0 warnings. Let me just minimize this a bit. Here is my hardware setup. All right, let me just put it up. All right, so here's the hardware setup. And let me go back to the Kyle Microvision IDE. Let me download the code to this board. And we have success. So programming is done, verify OK. So let me just bring my Term emulator, serial emulator. All right, so here it is. All right, so now if I go to my board here, if I go to my board here and I press the reset button, we should see Hello World on the serial terminal. Let me just go to press reset, and there we have it, Hello World. Let me just press it one more time. Right, Hello World, and one more time, Hello World. Now let's head over to the logic analyzer output. Okay, so this is the output from the logic analyzer. I've set it up so as you can see from the channel D0, these are the signals coming up from the transmitting pin of the TM4C series board. And here, the top part here is the protocol decoder output. All right, so you can make it up. You can see the message hello, HELLO space WORLD, hello world. These are the carriage return and line feed code. These 0D hexa and 0A hexa. So let me just zoom in a little bit. As you can see, these are the binary representation of the uppercase ASCII H, and these here, if I zoom in a bit more, think you can see it better here. A start bit and the stop bit. So much for the protocol decoder and the logic analyzer D0 output. Before I leave, just to point out again, you see this here, 1, and here is the signal from D0. That's representing a 1 here, and a 1 here is representing it. And these spaces here all represent zeros, 0, 0, 0. So you get spaces and 2 spaces here, 0, 0, and the last space here, that's a 0. All right. Okay, that's it for this video. Thank you for watching, and I'll see you in the next video. Bye.